Hello friends, our today's topic is plate tectonic. If we talk about Earth's surface, it is very dynamic, it is ever changing. If we look at our Earth's surface, at some places we'll find the Rockies, Andes, Himalayas, various mountain ranges, canyons, etc. will be found. But if we go around 200 million years back, then there would be no Rockies, no Himalayas. So it is a matter of curiosity. What would have been there around 200 million years back? There would be a supercontinent, a Pangea. What happened to this Pangea? This single large land mass, it would have disintegrated into pieces. And these pieces, over a period of time, drifted away from each other and ultimately acquire its present position, that is geospatial position. This was the basic idea of the Wegener. So when this single land mass disintegrated, number of oceans would have formed. So similarly, we can say in this manner, Indian Ocean or Atlantic Ocean would have formed. Or in similar manner, some oceans would have closed, like the Tethys Sea. So in a simpler way, we just want to say this, that there were lots of changes continues to occur on Earth's surface. Like Indian plate, strike with the Eurasian plate, and it becomes the part of the Eurasian plate. So on Earth's surface, continuously changes is taking place, movement is taking place, and that is resulting into earthquake, volcano, mountain building formations, and various other tectonic activities. If we look at our Earth, if we remove only the water part and we see the solid part of Earth, this is lithosphere. So if we look at the lithosphere, it is not a single land mass, but it is broken into interlocked fragments. So can you see it here? Suppose this is the our Earth surface. So if we see here, this one part, this is the another part. So this is the another part. So what we are observing, the interlocked fragments are there. So this interlocked fragment, we are calling it tectonic plate or lithospheric plate or simply plate. So lithosphere is not a singular landmass, but it is broken into interlocked fragment. This point is important, that it is interlocked. As we discussed in our earlier chapter, internal structure of Earth, we discussed that what is lithosphere? Lithosphere is what? Crust and upper solid part of mantle. If we say this is the outermost layer, this is the crust. This is the mantle. And we know that the middle part of the mantle is semi-solid, semi-liquid in state. This layer is what? Asthenosphere, right? Asthenosphere is what? We discussed it earlier. It is a plastic rock, a weak sphere. So lithosphere is what? Crust plus upper solid part of mantle. This part is lithosphere. And this lithosphere is floating over the asthenosphere layer. If you look at the lithosphere, here two component is there. Continental lithosphere is there as well as the oceanic lithosphere is there. So there is some difference in the oceanic lithosphere and the continental lithosphere? See, if we see just the oceanic lithosphere, see, in the center part of the ocean there is a ridge. This is the continent part. This is the continent part. And in between this is what? Ocean. So if we see its vertical segment, so what we will found? This is the continent part. See, this is the ridges in the ocean. And if you see the thickness of this oceanic crust, this is the oceanic crust, the thickness of the oceanic crust is increasing as we are moving away from the ridges. And ridges is what? It is the thinnest part of the oceanic lithosphere. And since it is thinnest, so can I say it is easy for the heat to escape from these regions? So the ridges are the thinnest part of the oceanic ridges through which continuously heat or magma comes out. And as we move away from the ridge, the thickness of the oceanic lithosphere is increasing. So this is what? Oceanic lithosphere. But by contrast, if we see the continental lithosphere, so how is it? Suppose this is the ocean, while this is the continent part. So on continent there is a mountain area. So wherever mountains are there, the thickness of the lithosphere is more. So this is how the continental lithosphere. So here I can say this, that oceanic lithosphere are thin, but in contrast to this, continental lithosphere is thick. It is somewhere around 100 to 150 kilometer thick. At some places it may be as thick as 240 kilometer, specifically under the oldest part of the continent. So if you see the map here, here is the Canada, this is the shield area. So Canadian shield. So shield is what? The oldest part of the continents which are tectonically stable. And they are tectonically stable because they are thick. So their thickness may vary till 250 kilometer. So is it clear the difference between the oceanic lithosphere and the continental lithosphere? And so where this lithosphere is floating? It is floating above the asthenosphere layer. Asthenosphere is what? A plastic sphere, plastic rock. So why the lithosphere is floating over the asthenosphere? Because the lithosphere is buoyant, it is less dense in comparison to the asthenosphere. So this is the reason it is floating over the asthenosphere layer. So here two things are important. One thing, lithosphere is floating over the asthenosphere, and lithosphere is what? Interlocked fragment. And when these interlocked fragments float over the asthenosphere, so continuous interaction will be there between the plates. Either the two plates will move towards each other, or two plates will move away from each other, or they simply slide past each other. So this gives rise to what? Tectonism. So basically what is tectonism? Tectonism is a building force. Building force means something is building. So question is, what is being built here? So here, due to the interaction between the plate boundaries, mountains are building, highlands are forming. So all this is give rise to the tectonism. So it is clear what is tectonism? Is it clear what is tectonic plate? What is difference between oceanic lithosphere and continental lithosphere? So till now, what we found that the whole lithosphere is fragmented into 7 major plates. If you look at the map, these 7 major plates are, see here, this is the North American plate. This is the South American plate. This one is the African plate. You can see it is the continuation part. This is the Eurasian plate. If we see the this here, this is the Central Indian Ocean Ridge, Southwest Indian Ridge. So here is the Antarctic Pacific Ridge and East Pacific Ridge, like this. So this part, this is the Indo-Australian plate. Indo-Australian plate. This diagram is very important. I'm just trying to show the major. See the one margin is here, and this margin is going here like this. Okay, so this is the Indo-Australian plate. And the last here is the Antarctica plate. Here this is Pacific plate. So these are the 7 plates. Presently, the lithosphere of Earth is fragmented into 7 major plates, and these 7 major plates are here in this map. This map is very important. And if we see this map, so one interesting fact is there, that except the Pacific plate, all the other plates have both component, the oceanic part as well as the continental part. If you see the map of North America, so this is the continental part and some part oceanic. If you see the African plate, continental, some part is oceanic. If you see the Indo-Australian plate, some part is continental, major part is oceanic. Only the Pacific plate is such plate which is completely oceanic in nature, and it major acquires the Pacific Ocean. So this is the location of the 7 major plates. So here I can say that the plate tectonic theory is an improvement over the continental drift theory of the Wagner, because the continental drift theory says that the continents are moving over the oceans, while the plate tectonic theory is saying what? It is the lithosphere which is floating over the asthenosphere. It means the ocean basin is also moving over the asthenosphere. So this is the basic difference between the plate tectonic theory and the continental drift theory. Besides these seven major tectonic plates, there are some intermediate size plates. So let's see the location of these intermediate size plates. So here is the Philippines plate. Philippines plate is here. Philippines plate. It is completely oceanic. So here you can see this is the Arabian plate. And Arabian plate is continental. Then here it is the Caribbean plate. Again oceanic. These are the intermediate size plate. Here is the Juan de Fuca plate. Juan de Fuca plate. Here the Cocos plate. Here the Nazca plate. And here is the Scotia plate. So these are the intermediate size plates. This diagram is very important as the margins of these plate boundaries where the major tectonic activities are taking place. So here the most important thing about these plate is all these plates are in relative motions with each other. Clear? So till now we discussed what is plate, what is tectonism. Okay? But here the major question is why the major tectonism occurs along the plate boundaries. Why not at the interior part of the plate? So the question is why major tectonism occurs at the plate boundaries. See, this lithosphere is made up of strong and rigid material. So it acts as an efficient stress guide. In simpler term, it means if a tension or a stress applied at the one end of the plate, then that tension will be transferred to the other end of the plate without any plate interior deformation. See, let's try to understand this. Suppose there is one tectonic plate here. Okay? So this part of the plate is getting heavier. So it is subducting downward. Due to the force of gravity, it is pulled downward. So stress is applied here. It is pulling downward. So if the stress is applying here, this end of the plate, then the tension will be transferred to the other end of the plate without any deformation of the plate interior. So the question is, why deformation is not there in the plate interior? Because it is made up of strong material. This is the reason. So now is this clear? So whenever any stress applied at the margin of the one plate, it will be transferred to the margin of the other plate, other margin of the same plate. This is the reason major tectonism, major tectonic activities are occurring at the margins of these tectonic plates. So hope this point is clear. Here we are talking about plate tectonics. We are talking about tectonism. And tectonism is what? a science, basically science. So here, in science we talk about the generalizations. So here our main focus should be on the plate boundaries. So we will focus on the plate boundaries. But here the question comes, how we will come to know that these plates are moving? That is the basic question. If we look at our map here, here is the North America. You know, here London is there. Here New York is there, right? So here Denver is there. Clear? So if we see through the satellite pictures, or if we calculate the distance between the New York and the London, and New York and the Denver, so what do we found? We observed that the distance between New York and London is increasing, while the distance between New York and Denver is fixed. So what does it shows? It shows that New York and Denver, they are on the same plate. And this is the reason the distance between them is not increasing. While the distance between New York and London is increasing. This shows that the two places are located on the two separate plates, and these plates are moving away from each other. They are diverging from each other. So this shows that two plates are moving away from each other. So is this clear? So when we are talking about the plate boundaries here, is this clear why we are focusing on the boundaries? Because the major tectonism occurs at the plate boundaries. So till now we discussed what is tectonic plate, what is tectonism. We discussed plate boundaries are there and they are moving. So now let's discuss types of the plate boundaries. Types of plate boundaries. So first is divergent plate boundary or constructive plate boundary. Second is convergent plate boundary or destructive plate boundary. And third is transform plate boundary or conservative plate boundary. So these all are the different types of the plate boundary. Clear? So if we see the distribution of the major earthquake, strong earthquake on the earth's surface, if we try to look it through the map, what we will find? Suppose, I'm just trying to show it through the map, the distribution of the major earthquake, areas. So just see here. Most of the earthquake occurs along the margins of the Pacific Ocean. So this is the boundary of the Pacific Ocean. 70 to 80% earthquake occurs in this area. Then this area, Trans-Himalayan region, mid-continental belt, this area where the major earthquake location is found, that area, mid-continental belt, then this mid-Atlantic ridge area. So this is the distribution of the major strong earthquake throughout the world. And what we are observing here, that their location is coinciding with the positions of the plate boundaries. Similarly, if we see the distribution of the major volcanism throughout the world, so again we know that major volcanism occurs around this Pacific Ocean. We call it ring of fire. Mount Mayon, Mount Fujiyama, Ojos del Salado, all these various volcanic eruptions are in this area. And this area, major volcanism occurs here. Mount Etna, Mount Sicily, Mount Stromboli are found in this area and this region, mid-Atlantic region. So in short, I can say the distribution of the major earthquake and volcanism are coinciding with the boundaries of these lithospheric plates. So this shows major tectonism occurs along the boundaries of these tectonic plates. So now let's discuss these boundaries in detail. So first is divergent plate boundary or the constructive plate boundary. So divergent boundary is when the two plates are coming close to each other. Divergent plate boundary means when the two plates are moving away from each other. This is divergent boundary. As we see, suppose this is the oceanic crust, this is the continent part, and in between is the ocean is there. So here what is happening? Tensional forces is there. Two plates are moving away from each other. So this is the middle part of the ocean. So in between is the ridges. So if you see its vertical section, the two plates are moving away from each other. So this is somewhat the situation wherever the divergence is taking place. Divergent plate boundary. Second case is the convergent plate boundary. So convergent plate boundary or destructive plate boundary. So this situation occurs when the two plates come close to each other. When the two plates are coming close to each other. So right? So in this case, two cases may be possible. The convergence may be simply collision, or second case is by subduction. One plate is subducting under the another plate. For example, this is the oceanic plate which is subducting under the continental plate. So here is the ocean part, here is the continent part. This is the lithospheric plate. So this oceanic plate is melting here. So here what is happening? Subduction is taking place. So if we see the example of the divergent plate, so can you see this Atlantic Ocean here? This is the mid-Atlantic ridge. So here the American plate is moving away from the Eurasian plate. American plate is moving away from the African plate. So this is the example of the divergent plate boundary. And the example of convergent plate, can you see it here? South America is here. So here along this boundary, what is happening? Subduction is taking place. Subduction of the Pacific plate is taking place here. So this is what an example of the convergent plate boundary. The whole area surrounding the Pacific Ocean. So it is the example of the convergent plate boundary where the two plates are striking with each other. Clear? Third case is transform plate boundary. So if we see the transform boundary, so here two plates are neither moving away from each other. Third is transform boundary. Transform plate boundary or conservative plate boundary. So here what is happening? Two plates are neither moving away from each other nor coming close to each other. They are just sliding past each other. So here neither construction is taking place nor destruction is taking place. Margins are conserved. So it is known as conservative boundaries. Clear? So here question may arise, is there a probability that all these three type of boundary can be found along one particular plate? Yes, this can be the possibility. If we take the example of the North America, so here is the Juan de Fuca plate is there, right? This boundary is what? Divergent boundary. This dotted part is divergent boundary. Okay? And these divergent boundaries are connected together by transform boundary. Clear? And on its other part here, this is here what is happening? Subduction is taking place. It means convergent boundary. So this plate is what? Juan de Fuca plate. So at one plate, all the three boundaries is there: divergent boundary, transform boundary and the convergent boundary. So these are the three types of the plate boundaries. Clear? Now we will discuss in detail what is happening and at the particular boundary. So first we will take the case of the divergent boundary. See, first case is divergent plate boundaries or constructive plate boundary. Divergent plate boundary, constructive plate boundary. So these are the boundaries where two plates are moving away from each other. The two plates are moving away from each other. So where do we found such kinds of boundaries? Yes, along the crest of the oceanic ridges. So again, if we see the diagram here, see the map, wherever ridges are there, we will found the divergent boundaries. So there is a long network of ridges in our oceans. So can you see it here? The most important is this mid-Atlantic ridge. So this is the area where the two plates are moving away from each other. Mid-Atlantic ridge. Mid-Atlantic ridge. So here what is happening? Two plates are moving away from each other. And if we see On the Earth's lithosphere, there is a continuous network of the ridges. So this ridges is continue here along the Indian Ocean. So can you see it here? Central Indian Ridge, this is Southwest Indian Ridge, Southwest Indian Ridge, here Southeast Indian Ridge, which is continues as Pacific Antarctic Ridge. And this is again further continued here as East Pacific Rise. So there is a Hawaiian Ridge. So here can you see there is a continuous long network of the ridge, Mid-Atlantic Ridge, Southwest Indian Ridge, Central Indian Ridge, Southeast Indian Ridge, Pacific Antarctic Ridge, East Pacific Ridge. It is somewhere around 70,000 kilometer long continuous network of ridge. So these ridges are what? They representing the divergent boundaries. Here the two plates are moving away from each other. So let's see what is happening at the divergent boundary. If you see the map here, so here in center is the ocean basin is there and ridge is there. So if we see the map vertical section, right? So what is happening? Just below the destructive plate margins. So as the two plates will move away from each other, a gap or a fracture will be developed. This gap or fracture will be filled by the hot molten magma which is just below the fracture. See, this is the situation here. Here this is magma, molten rock is there, molten rock magma is there. So through large number of basaltic dikes, these are what? Dikes. Basaltic dikes. This magma will oozes upwards and fill this gap. It cool down, solidify, and the new oceanic lithosphere will be formed. So construction is taking place here. So this is the reason this boundary is also known as constructive plate margin. So can I say the divergent boundary is what? Spreading zone, where continuous upwelling of the magma is taking place and which is solidifying, and a new oceanic crust is added to the diverging plate. This is happening here. But here the question is, why volcanism is taking place here? What is the reason? Why the volcanism occurs just below the divergent boundary? So in order to understand this, let's take some material. Question is, why volcanism occurs just below divergent boundary. To understand this thing, let's take some matter. Now apply pressure to this matter. So what will happen if I apply pressure to this material? It will contract. If I further apply pressure, so it will contract further. Clear? Now tell me what will happen to its melting point? Yes? Its melting point will increase. It means what? Now we need more heat to melt this material. Clear? Now let's do one thing. Now release this pressure. Remove this pressure. So if we remove this pressure, then now tell me what will happen to the melting point of this material? Yes? Can I say its melting point will decrease? Yes? Can I say now I need less heat to melt this material? Agree? Okay. So same thing is happening along the divergent boundary. See, what is happening actually? This is the divergent boundary. This is the divergent boundary. Right? Because of the diverging plates, a tensional force will be generated as the two plates are diverging. These plates are diverging. So what will happen? Tensional force will be generated, and due to this tensional force, fracture will be developed here. Fracture developed here. Clear? Fracture is developed here. Now tell me, what will happen to the pressure of the rocks just below the fracture? The pressure will be released. The pressure will be released means now what will happen to its melting point? Whether it will increase or it will decrease. Yes. Since the pressure is released, here melting point will be decreased. So can I say this rock will melt and it will oozes upwards, fill this gap, cool down, and a new oceanic lithosphere will be formed? Clear? So this is happening. So is this clear? Why volcanism occurs just below the divergence plate boundaries? Clear? So in short, I can say the divergent plate boundary is generating the tensional force due to which fracture is being developed that leads to the lowering of the pressure and lowering of the melting point of the rocks that triggers melting of this rock and which emplaces the fractured and a new oceanic lithosphere will be formed. So is this clear? So this is what is happening below the divergent plate boundaries. And a new oceanic lithosphere continuously forming. So we can say sea floor is spreading. Till now, what we observed, the major divergent boundaries are found over the oceanic lithosphere. Oceanic lithosphere, right? So can it be found over the continent? Yes, it can found over the continent also. Now let's see what is happening if we found divergent boundary over the continent. Let's suppose this is our crust, mantle, core, right? And this is the continental plate. Crust, mantle, core. And our core is very hot. Crust, mantle, core, right? Core is very hot. Temperature is very high. So core wants to cools down. So it will be easy for the it will be easier to lose heat through the oceanic crust, because oceanic crust is very thin. But it will be difficult to lose heat below the continents. Why? Because continental crust is very thick. So what happens? Heat is accumulating here. And since heat is accumulating here, so hot spots will be created here. So hot spots are what? Hot spots are nothing. These are the high temperature zone areas. Hot spots will be created here. And these hot spots, where the temperature is very high, it will cause melting of rocks and a plume of mantle will be formed. Where? Below the continents. So now let's see what is happening below the continental crust. Because of the development of the hot spots below the continents, the folding of the continent will take place. As the plume will rises upward, it will cause bending of the continental crust. So let's see, let's try to understand this with the help of the diagram. See, suppose this is a continental block. This is the continental block. And a spreading center develops over this continent. So accumulation of heat will be here. A hot spot is generated here. Why? Because it is not easy for the heat to escape, so heat gets accumulated, resulting into the formation of hot spot. So this hot spot, it will cause the bending of this continental lithosphere. So see, what is happening? So along these hot spots, a mantle plume will be developed. This plume will rise upward. So this will cause bending of the continental lithosphere. So continental lithosphere will bend like this. So upwarping will take place. So what is happening here? Upwarping is taking place. Upwarping. And we know that lithosphere, continental lithosphere, is basically made up of the strong and the rigid material. It is brittle. And what will happen if we bend any brittle material? It will break. So here breaking of the continental crust will take place. So see here what is happening. So this is how this is the continental crust. This is the continental crust. And what happened? A long trough is formed here. And such long trough we call rift valley will be formed. Why this is happening? Because of this mantle plume. This is happening. So rift valley will form. So along such rift valley, it may collect, some water may be collected here, so some lakes may form here. So this thing happens when a spreading centers develops over the continental lithosphere. So can I say that in this similar manner, the Pangaea's, Wagner's Pangea would have disintegrated? If we see where present day, where we can find such situation, if we see the example of the African Rift Valley, so there is a long rift valley here. This is the long rift valley here. So this is at this stage, rift valley. And along this rift valley, what is happening? There are large number of Lake Victoria, Lake Winnipeg, Lake Tanganyika. So this is what? East African Rift Valley. So can I say that here a spreading center is developed? Over a period of time, if this process continues, this rift valley will become deeper, longer and widen. If this process continues further, then at one time it will come in contact with the ocean and water will be filled in this area and a linear sea would be formed. So this, what will happen here? If this process continues, so a linear sea will be formed here. So continent gets separated, right? In between, water is being acquired, a linear sea is formed. And why all this is happening? Because of this mantle plume. This is the linear sea is formed. I mean to say, over a period of time, when this rift valley will come in contact with the ocean, the water will acquire in this area and a linear sea will be formed. And this single landmass will disintegrate into two. This is what we call continental rifting. So in this similar manner, the Wagner's Pangea would have got disintegrated and a large number of the linear sea would have formed like this. See, a linear sea is here, a linear sea is here, which later on, when this process continues further, so these linear sea later on converted into the oceans. So this is how the changes has been taking place over a period of time. So present day such linear sea, you can find it here. If you see the map of Africa here, so this is the Red Sea. This is the Gulf of Aden here. So if we see the map, this Arabian plate can be easily fixed into this part of the Africa. So this shows that earlier these two are the single landmass which later on disintegrated and a linear sea is developed. And if this process continues further, a new ocean basin will be formed. So if this process continues further, so next stage is what? The ocean stage will be formed. So here this is how ocean will be formed. This is the continent part. This is the continent part, right? So here in between, a new ocean base is formed. New ocean basin is formed. This thing will happen. So this is what we call ocean stage. Ocean stage. This is a linear sea stage. So see what? We started with the divergent boundary over the continent. And we ended up into the divergent boundary over the oceans. So the divergent boundary which develops over the continents, ultimately they end up over the mid-oceanic ridges over the ocean floor. So this is how changes taken place over the continent. If some spreading centers develops over the continent and one single land mass split into the two land masses, this is continental rifting. And once the two continents separated, and if they move away from each other, we call it continental drifting. So is this clear? So till now we discussed divergent boundary, what volcanism occurs below the divergent boundary. We discussed what is happening in the ocean, over the ocean floor, and we discussed what happens if the divergent boundary develops over the continent. Clear? But here again the question is why the divergent boundaries are always represent with the ridges or a plateau topography. See, the divergence boundaries, along the divergent boundary, heat is continuously escaping out. So the temperature is high there. So if the temperature is high, so material is in the expanded form, right? Question is why divergent boundary represent a ridge or a plateau topography. See, along the divergent boundaries, since the continuously heat is coming upward, so material remain in a expanded form. And if material remain in a expanded form, so a bulge will be there. And when it will cool down, so some contraction will be there, reduction in the height will be there. So here the two situations can be possible. So what are those two situations? Let's take the first case. First case. If sea floor spreading rate is fast, suppose this is our ocean basin. If the sea floor spreading rate is fast, then what will happen? This hot magma will get displaced away from the ridge before it sufficiently cooled down. Why is it happening so? Because the sea floor spreading rate is fast. So in such case, it will give rise to a plateau topography. It will give rise to a plateau topography, right? But second case, if the sea floor spreading rate is slow, suppose this is our oceanic crust. If the sea floor spreading rate is slow, then what will happen? The magma will remain at its own place. It will sufficiently cool down before it is displaced away from the ridge. So it will give rise to the ridge or a mountain topography. So is this clear? When the plateau topography will be there or when a ridge or mountain topography will there, it depends on the sea floor spreading rate. If the spreading rate is fast, the hot magma will get displaced away from the ridge before it sufficiently cooled down, so give rise to the plateau topography. And if the seafloor spreading rate is slow, then magma will sufficiently cool down before it gets displaced away from the ridge. So in that case, it will give to the ridge or the mountain topography. So this is all about the divergent boundary. Clear? Now let's come to the convergent boundary. So next is convergent boundary. So convergent boundary is where the two plates are coming close to each other. So just now we saw this world map. Convergent boundary is along the Pacific boundary, Pacific plate boundary, circum-Pacific region, where the Pacific plate is subducting under the Eurasian plate and the American plate. Subduction is also taking place in the Antarctic Ocean also, along the Caribbean Trench or the Sandwich Trench. This convergence is taking place in the Indian Ocean also. So in Indian Ocean there are basically three types of convergence. It is continental also, some portion is continental oceanic, some is oceanic convergence. So let's discuss convergent plate boundary or destructive plate boundary. Clear? So here two plates are coming close to each other. So here two possibility is there. One is by simple collision. Plates are simply colliding, or by subduction. One plate is subducting under the another plate. So in case of subduction, there can be possibility that oceanic plate is subducting under the continental plate, or oceanic plate is subducting under the oceanic plate. While in case of collision, there are three cases may be possible. Continental plate is colliding with the continental plate, continental plate is colliding with the oceanic plate, or oceanic plate is colliding with the oceanic plate. So when it comes to the subduction type, here what is happening, suppose this is the oceanic plate. So this oceanic plate is subducting under the continental plate. This is oceanic plate, this is the continental plate, lithosphere. Right? When the oceanic plate subduct its lower part, it starts melting, and that will give rise to the mantle plume also. So here subduction is taking place, right? So here question is, why one plate is subducting under the another plate? Second question, why never continental plate subducts? Always oceanic plate subducts. So regarding this thing, if we look in our traditional books like Savinder Singh and various other books, it is mentioned that basically the convection currents in the asthenosphere layer is mainly responsible for the subductions of the plate. But now our understanding with respect to the subduction is changing. Now most of the scientists also agree that besides the convection current, it is the some other force. What is that? Slab pull force. Slab pull force is mainly responsible for the subduction of the plate. So in order to understand this slab pull force, let's first compare the density of these plates. Density of the oceanic plate, density of the continental plate, and these both the plates, they are floating over what? The asthenosphere. So here is the asthenosphere. This is the oceanic plate. This is the continental plate, right? Three things are there. So now let's compare the density. Density of the continental lithosphere is 3.1 gram per centimeter cube. Density of asthenosphere is 3.25 gram per centimeter cube. Density of oceanic lithosphere is 3.28 gram per centimeter cube. These are the density. So now see, now this is clear from this fact why never the continental lithosphere subducts into the asthenosphere. Why? Because continental lithosphere is buoyant with respect to the asthenosphere. Its density is less with respect to the asthenosphere. This is the reason continent always floats over the asthenosphere. They will never subduct. Now come to the oceanic lithosphere. So see, when along the ridges new oceanic crust is forming, it is warm, its temperature is high. And we know that when the temperature is high, density is low. So that time oceanic lithosphere density is less than the asthenosphere. So this is the reason oceanic lithosphere floats over the asthenosphere. Clear? Suppose this is here is the oceanic ridge. Oceanic ridge is there, right? So here what is happening? Because of the heat, continuously heat is coming out, new oceanic lithosphere is forming here. So here temperature is high, so oceanic lithosphere density is low with respect to the asthenosphere. So oceanic plate is floating over the asthenosphere. But as the oceanic lithoplate will move away from the ridge, it will get cooler. As it will get cooler, it will get denser. So at one point, its density will become more than the asthenosphere. So as the density of the oceanic lithosphere will become more than the asthenosphere, so oceanic lithosphere will become heavier. So due to the force of the gravity, it will be pulled downward. And at that moment, it will start subducting into the asthenosphere. This is the slab pull force. So this is the main driving force that is mainly responsible for the subductions of the older part of the oceanic plate. Hope this is clear. What is slab pull force? So again, see, convergent plate boundary. Again, the topic is very big. So till now, we have covered the major segment. We will continue this topic in our next video. Hope till now, whatever we have covered is clear to you all. Thank you. Thank you so much.